So welcome to the University of Adelaide's Electrical and Electronic Engineering 1A in-practice tutorial for Module 2, Part 3. Today we're going to be discussing flip-flops and flip-flop behaviour. Firstly, we really want to remind you to just check the data sheet. Data sheet for that is the 4013. There's a couple of basic facts about the flip-flop that we need to know. One is it's basically an electronic latch, okay, which means it's used to connect signals, connect pins from different devices as certain locked instances. Next thing we need to know is it's used, sometimes used for a data buffer, to buffer data in digital circuits. We'll learn more about that in secondary subjects. And a couple of really simple rules about its behaviour. Rule number one is that at the positive clock edge, that is as time on a clock pulse, on a clock square wave, at the positive clock edge, Q becomes equal to D. So the Q pin, which is an output, becomes equal to whatever is on D, which is commonly known as the data pin. Another rule to remember is the set and the reset pin can be used to force the flip-flop into a defined state. And rule number three, Q is always the inverse of Q bar, except of course when rule 2 has come into play. And the fourth rule that we want to remember is that at the negative clock edge, there is no change in the circuit. Okay, so as an example for that, I want to go through and discuss this particular circuit here that's sketched up. We're going to go through what's called a timing diagram for this circuit. This is just a timing divider. So here I have my clock square wave that I've drawn already. I've got half the first time slice drawn. Here with D, I've got Q that's already set to high and Q bar is set low. So D is going to propagate all the way through to here. So if D is high for this particular cycle, then Q bar must also be equal high, or rather the other way around, as they're connected electronically, which means that Q must be the inverse of Q bar. And then we hit, at this instance, we hit the next positive clock edge. So at this instance here, Q becomes equal to whatever D is, so it will go high and stay there for the next time slice. Q bar is always the inverse of Q, that's what the bar means, so this will go low and step across, and D being equal to Q bar will track whatever Q bar is doing, so on and so forth. So at this instance, Q here will become equal to whatever D is, which is low, propagate across, and then Q bar will be the inverse of whatever Q is, and then D will track whatever Q is, and so on and so forth. As we can see here, this signal will just keep propagating through, like so. And I'll leave it there. This is what's called a timing diagram. You can use it to analyse all different types of circuits, with latch circuits. It doesn't have to be this, you can use any circuit arrangement. They're very, very handy when you're trying to analyse what's going on and a sequence of events in a latch circuit. Thank you.